These are called De Morgan's laws. So these are double sequence. They mean that you can prove the sentence on the right, assuming the sentence on the left as a premise. And you can prove the sentence on the left if you assume the sentence on the right as a premise. There are two of De Morgan's laws. One, the interderivability of neither P nor Q with both not P and not Q, and the interderivability of not both P and Q with either not P or not Q. And obviously these are very straightforward entailments. We can easily see that they're valid. The proofs of them require reductio. So the first one, we do the left to right proof. We assume neither P nor Q. And we set about proving not P and not Q. Well, not P and not Q is a conjunction. So if we can prove not P and we can prove not Q, then we can just put them together on the last line to make the conjunction. And to prove not P, we use reductio. We assume P. Immediately we get either P or Q from 2 by wedge introduction. And 1 and 3 contradict each other, they're denials, and so we discharge 2 by denying it, not P. 2 drops out of the assumption set, and so from the sentence on 1, we have proved not P. Now we do the same thing with Q, an assumption for reductio. We use wedge introduction again, either P or Q. 5, wedge introduction. You can tack on a left disjunct or a right disjunct. 1 and 6, reductio, discharging 5 by denying it, not Q, and then we put the 2 together, not P and not Q, for 7 ampersand introduction. And so that is the left to right proof. What about the right to left proof? Well, here we're assuming both not P and not Q. And we want to prove neither P nor Q. Again, reductio. We assume either P or Q. And now, well, if we take not P from 1, ampersand elimination, then we have either P or Q, but not P, so Q. 2, 3, wedge elimination. Then we take not Q from 1 ampersand elimination. And now we have 2 sentences on 4 and 5, reductio, they deny each other, so we discharge 2 by denying it. 2 was either P or Q, so what we get is neither P nor Q. And that is the proof of the right to left sequent. So these 2 proofs together, the left to right one and the right to left one, prove the first of De Morgan's laws. Very similar kinds of proofs will prove the other law too. What's interesting about these two proofs is that we could put them together in one long proof and prove a theorem. So suppose instead of this assumption here as a premise, we'd assumed an assumption for arrow introduction. Then on line 9 here, we could discharge our assumption on 1, and we would get this conditional. So we would say 8 arrow introduction discharging 1. The sentence on 1 becomes the antecedent of a conditional that has the sentence on 8 as its consequent. And the assumption set has gone empty. Now we could run the right to left proof. An assumption for arrow introduction. We assume either P or Q for reductio. So here I'm just copying this proof into this one here. Not P, 10 ampersand elimination. So that's the same as the step there. Q, either not P here, sorry, either P or Q here, not P here. So Q, 11, 12 wedge elimination. Not Q from 10 ampersand elimination. And then the reductio, 13, 14 reductio, discharging 11. And now we get neither P nor Q proved on 10. Now we discharge 10, we get the conditional. So not P and not Q becomes the antecedent, neither P nor Q becomes the consequent, and that is 15 arrow introduction discharging 10. And again, the assumption set goes empty. Now, here is a conditional proved as a theorem on the empty set. If neither P nor Q, then both not P and not Q. And here is a conditional theorem proved again on the empty set. If both not P and not Q, then neither P nor Q. And they can be put together then to make the biconditional theorem. And that's 9, 16 double arrow introduction. And here we have a proof, a theorem proof. We have a proof of this sequent, the biconditional theorem. So the last line of this 17-line proof corresponds to this theorem. It's a theorem that puts the biconditional between two interderivable sentences. So every time you can prove one of these double sequents, you could also go further and prove a biconditional that takes the place of the double turnstiles. You could prove that as a theorem.